Good afternoon. Welcome back after the lunch break. And welcome to my amazing talk of in-guest device emulation. It was a fun pet project that I've started off, and we're going to have a buff later on to see what we can do out of this and where can we drag it. So first off, who am I? My name is Graf. I just recently switched over to Amazon in May this year. You might remember me from projects like Nested SVM or PowerPC KVM or random other fun things I've done in the KVM world. What I'm telling here is all my own opinions, obviously, typical disclaimer. So what is device emulation? Well, how does device emulation usually work? What do we do there? This is a bare metal machine. On a bare metal machine, you have user space that talks to kernel space, that talks to hardware, and then you have really, really normal interfaces as long as you have a reasonably non-DBDK, SPDK interface to your system. When you introduce virtualization, what we usually do is QEMU there in the KVM world. When you introduce virtualization, this changes to this picture. So you still have user space and kernel space there, but when the kernel tries to access hardware, we no longer allow direct access to hardware. We route that via KVM into device emulation that commonly lives inside of QEMU, inside user space on the different world, the host world. The problem with that is if there's a bug inside of that emulation code, which obviously never happens, but if there's a bug, then you suddenly have an entrance door for malicious code in another area that you did not necessarily expect it to be in, which means you may get into security issues because the attack surface is just much bigger than what the guest had before when it was just running directly to hardware. This whole virtualization thing is actually not terribly new. IBM has done it forever, and even on X86, it's been around for a while. So who of you knows what SMM is? Who of you shrugs in fear when they hear of SMM? Very good, very good. So SMM has been introduced to solve a very similar problem on real machines on bare metal. Imagine you have a kernel. I'm drawing Linux here, but it's not really meant for Linux. You have a kernel, and that kernel wanted to, for example, talk to hardware using a PS2 keyboard controller. Now, unfortunately, the world moved on, and we started plugging USB keyboards into our systems, which don't have a PS2 keyboard controller anymore. So how do you bridge that gap between an operating system that talks to your legacy keyboard controller and a USB device that you need to drive? Well, Intel figured SMM is a really smart way. We introduce a piece of code in firmware that simply you trap into whenever you want to talk to your keyboard controller, and then translates that into USB commands down there, or arbitrary other things. There's a lot of value add in SMM for definitions of value add. So how does QEMU device emulation work? We're just going through quick history 101 so that we can combine the different pieces of the puzzle afterwards. What does QEMU device emulation look like? In QEMU device emulation, we went through that earlier, right? So you have user space, you have kernel space, then you have on the host, you have KVM, you have a KVM user space, and you have hardware that is under control by the host. So when the guest wants to try and actually talk to hardware, it instead doesn't go to hardware, it goes into KVM, causes a VM exit, which flows into user space using an octal exit. Then user space can go and actually do an operation like a read. It says read, yes. Like a read, which goes into the host kernel, which then can translate into a real hardware interface, like say an NVMe command, down to hardware, which then returns into the kernel because the hardware finished reading that data, and then you go back into your user space, which then can run the octal to run the guest again, and so you can go back into your guest context to finish the operation you were just triggering off. That's the simple emulation path we always do for pretty much every device we have. There's a couple of alternatives to it. Sometimes you can do things asynchronously, but in a nutshell, you're going through all those layers. You can do shortcuts. If you do direct device assignment using, say, VFIO, instead of taking hardware into responsibility of the host, you pass it straight onto the guest, so the guest has full control over hardware. Which means when you now do a hardware command, that hardware command can actually go to hardware. Sounds much easier, right? Well, there's a caveat. The biggest problem that you have there is that suddenly you actually talk to hardware. which means the guest needs to be aware of how to talk to that hardware. You cannot emulate interfaces in between. You can't just do virt.io on that hardware unless you actually own the hardware as well. You can, however, combine those two approaches even. So there have been people and approaches. You've probably seen Felipe's talk on how to accelerate device emulation using SPDK. There are approaches where you can have user space on the host, directly own that hardware, so you at least circumvent the kernel layer in between. And then your device emulation still goes from the guest kernel into, or your device accesses still go from guest kernel onto KVM into that user space, but then you don't have to go all the kernel route on the host again, which can accelerate things quite a bit. Now, if you keep thinking that train of thought, if you think, well, I have a user space process that can actually dedicatedly access hardware, and I have hardware that can be virtualized, and so I can have different virtual functions for my different tenants on my system, for my virtual machines, why don't I just put all of that code that still gives me the big attack surface, why don't I just move all of this code into the guest? The interface to have a guest access hardware is already existent. We have VFIO, so the piece down here is easy. We do have traps when we try to access code, so maybe we can just actually push all the emulation code to translate from one interface to another into guest context itself. The nice benefit of that would be that if there's a bug in that code, well, your attack surface kind of is the exact same as if the guest had a bug, so you don't necessarily escape the guest boundary into another guest on the same host. Make sense? Okay, let's walk through how this would work. So let's look at a PIO request. Port.io request, typical x86 thing. You have an outl out there that the Linux kernel would trigger. That outl would go and spawn a VM exit, so you're running in KVM context now, and inside of KVM, what we can do is we can just inject an SMI into the guest instead of handling that port.io request, which gets us into a completely different context inside of the guest, into SMM context inside the guest. Now, once we're in SMM context, we can start to do whatever we like based on that port.io request, say an MMIO over to hardware that goes into real hardware, we finish it. You spawn an RSM at the end to return from that system management mode back into a normal guest operating system, and that gets us back into the guest. So there we basically have the same switch that we had before with QEMU, just that instead of switching from guest to host to user space, we switch from guest to host to guest SMM mode, and then back. MMIO is more fun. MMIO, same concept. You basically have a move, some access to memory, and you want to also trap that. The way this gets trapped is that in KVM, we actually have a VM exit on a page fault, on a nested page fault. Because the way MMIO gets handled is that we basically assume that pages that are not backed by memory are all handled by hardware. So we now have a page fault inside of KVM, and we don't know anything beyond that page fault. We just know somebody was trying to access memory at an address that didn't work. Sometimes there's some hints, but usually it's pretty secretive. So we can still inject that SMI into the guest, but now there's this additional piece of code that we need to run, which is called an X86 Animator, which usually happens to live inside of KVM. But using that technique, we can now move it from this really, really privileged world over here in KVM in the host kernel over into this really, really unprivileged world, which is inside the guest context in the enclave that we just created. So we take a lot of attack surface and move it all the way into the guest itself. That x86 emulator can translate it over into a request that we can handle, the device emulation code can parse, that can cause a reaction, say I need to do another MMIO onto my real hardware, and then you just go back into the host, which then does, using the RSM trap, goes back into the guest into normal execution mode. The most interesting part in my book, or the most surprising one from my point of view, was IRQs. So we also have the other path around, that a device wants to tell you, well, I do have new data, you should really pick that up. How do you pass that on to your guest when the interface is completely different from the real hardware you were passing through? Well, it turns out there's a nice interface. MSIX, pretty much every hardware these days uses MSIX. And MSIX has a feature where you can tell MSIX, well, don't target a normal vector, just target SMIs, right? You can actually configure your MSIX vector to directly inject an SMI into your guest. Well, so we inject an SMI based on KVM. KVM gets that interrupt, right? And injects an SMI into the guest for us. Done deal.
Can you use the menu to remap the SMI to a host?
So, Paolo was asking if you can use the IOMU to remap the IRQ to a host IRQ?
So you program the SMI, but actually the IOMU injects a host IRQ.
Wait a second. So I got the microphone to talk for the audience. How about we just do this after the presentation, and then I run over to you and you just ask. Awesome. So we get through all 79 slides. Why do you want to do this? There's a couple of benefits. The most obvious one that I was stressing all over is security, right? You basically take your evil attacker that can go and attack your user space, so you have to secure two boundaries. You have to secure the host and guest boundary as well as the user space host kernel boundary. You suddenly take all of that attack surface and push it all down into the guest, which means you only have to worry about a single attack surface at this point anymore, the host guest boundary. But there's more. So we do have things like hyperthreads, and one core usually on x86 happens to have two of those. So what happens when you have two hyperthreads and you have a guest and a host running? Well, as long as those two hyperthreads run inside guest context, everything's fine, right? The guest can possibly maybe leak data or influence the other sibling thread of the guest, but that's usually okay from a host point of view. The big problem is that when you exit that guest, what happens? Well, as long as you're in KVM context, there are some there's some progress with address space isolation and such, where you can actually be reasonably sure that as long as you are handling some exit inside of the host, you are safe. But as soon, at least, I mean, you basically guarantee that as soon as you go out of the KVM context in the normal general purpose Linux and even worse into user space, you open up spectre gadgets all over the place. And you can basically leak data from the whole host operating system over into the guest, which basically means you could possibly leak data from another virtual machine or from another host, or process that's running on the host over into your other thread. There are some mitigations on it, and you can isolate the problem set. But the basic fundamental problem still stands that device emulation code needs to essentially move your other sibling hyperthread out of execution as long as you're running in the host. Now, if we move all of that emulation code into the guest, well, worst thing that happens is you suddenly leak guest data. You never have the ability even to access anything on the host because you're still confined into your guest environment. So security-wise, this is even better because there's just simply no spectre left to worry about in that path. Another interesting side effect of it is, imagine you have live migration, right? You want to move a virtual machine from one host to another host. That usually means that you need to serialize all of the information that you have that describes device state, that describes CPU state, memory state, et cetera, et cetera. So you have to serialize guest state, like CPU, memory, and such, and then you also have to serialize device state that lives in that user space piece. Now, if you move your device emulation into guest context that lives in guest register space and that lives in guest memory space, it basically means you get all the live migration abilities for free. You don't have to serialize your device emulation code anymore. It just automatically gets serialized and transferred. So you don't have to worry about live migration. It just works. But it's not all nice and dandy. There are a couple of downsides. The most obvious one is what happens when you encrypt all your memory. How do you define the trust boundary of, I want to have a guest kernel that can now define that it no longer wants to have anything else look at the guest context, but then we do have to have device emulation code in the guest, which looks at guest context code. It gets difficult. I'm sure it's a solvable problem. We can certainly talk about that one on the above. Nested virtualization, you basically need to start introducing nested information into your SMM handling so that SMM can be potentially triggered when you're nesting because you might trigger an SMM exception, say an MMIO handling, a pod IO handling, while you are inside of a nested guest. So that in order to resume that again and to actually interpret all of the page tables within that, you need to start worrying about nesting more than you did before. And then there's the loophole problem. It's not a really big one. You can possibly do that before already. But you essentially give another attack vector to an attacker to inject code that is invisible from the guest itself. It's possible without that virtualization technique, so you can do that without as well. You can run something like a VMware binary translator in the guest, and it wouldn't see that it's actually getting binary translated, but this one is much more stealthy. So there's some minimal problematic scenario there that you can think of. The proof of concept that I just quickly hacked up is an IDE on NVMe emulator. So imagine you basically want to have an IDE adapter exposed into the guest, but the host only has an NVMe adapter. So this is a screenshot of what I did. You can basically pass through an NVMe device. Up there, I actually passed through a real NVMe device using VFIO. So this is driving a real NVMe adapter. And inside the guest, you can see it shows up as SDA. So it actually runs all of QEMU's IDE emulation code inside of guest SMM code to then expose an IDE device to the guest without the guest even noticing. It's just a firmware module, which I can show you. So I have another 2 minutes to give you a demo. Let's hope, pray to the demo gods. So this is the demo. It's the exact same command line that you saw before, same machine even. I'm basically just running an EFI module in a normal virtual machine that injects my device emulation code. And then I just pass through this NVMe device from the host into the guest where I preloaded an operating system onto it. So you see EFI boots up. It loads that EFI module from network, which then gets executed. So that won't scroll through too quickly. So there it got executed, gives you a bit of debug output. And inside of the boot manager, you can now see that we actually have an IDE drive exposed inside of EFI in the guest, even though it is originally an NVMe device, which can boot just fine. So let me just quickly. Does it work? Yeah. The screen is way too big for me. So we can now just boot up a normal Linux operating system, hammering on the IDE drive. It actually looks like a normal IDE device. It performs about as well as you would expect from an IDE device. Performance-wise, IDE is terrible either way. You don't actually realize the emulation code in there. So with that, any questions? I can run over to you with a microphone, and then you can have questions. So Paolo had the first one.
So the target SMI entry is set in the virtualized MSIX table, right?
Say again?
So the target SMI field is set in the guest's virtual MSIX table. How does that map to an IRT in the interrupt writing table entry?
It doesn't. So for SMIs, you cannot do IORTs because you basically don't get posted interrupts for those SMI vectors. That was the patch I sent a couple of weeks ago. You cannot do SMIs with IORT because IORT can only inject normal interrupt vectors. Okay. So you basically have to trampoline that via a host interrupt vector that is not SMI.
Okay.
And so the SMI path only happens inside of KVM.
So the host doesn't use the interrupter mapping for this?
Correct.
Okay.
You cannot use interrupt
rephrasing
mapping.
of my question.
Yeah.
So performance was missing on your downsides, but you did mention that it achieves IDE performance. It seems like a pretty big latency hit, though, to trap through SMI. Can you discuss any general performance versus direct assignment?
Let's think this through a bit. Do you have to trap through SMI?
Your example showed it.
You have to trap through
MMIO.
SMI for the prod.io requests that go to KVM. But that's the exact same distance as the QEMU user space is, especially if you take all the spectre mitigations into account, where all the switches become much slower again, right? However, for the device to guest injection, you don't necessarily have to use an SMI. You could actually reprogram it as a normal interrupt vector inside of the guest, because you do know that the first request you get will be a port.io request to figure the device status or the interrupt status of the device, at which point you can lazily adapt to the interrupt. So you don't necessarily have to, you can actually inject an NVMe finish interrupt as a normal vector into the guest, at which point you actually get an IORT mapping again.
The MMIO path was really the
In the
concerning
MMIO
one
path,
with
you have
the
to have it.
emulation in the SMI code.
Correct. So for the MMIO and port.io paths, you have to trap into the guest. There's no way around it. But again, it's the same as trapping into QEMU and like going back from it. It's a bit more latency. It actually is a slowdown in comparison to just a pure user space path. The question is just how important is that? This is mostly for legacy devices. At least that's what I envision it for. And from those, performance is definitely not on the critical path, especially not the latency of the instructions. It's slow either way. It's even slower on real hardware.
Basically, a segue into that. Did you look into using something other than SMI specifically so that you could enlighten the guest and do a direct, instead of doing the out, for example, do a direct call or jump or some form of control transfer?
Don't take away next year's talk.
The reason I ask is
there's a couple of
touching
techniques you
very
could
similar
use.
code in very, very similar ways for completely different reasons.
Interesting.
But
So there are other ways you can use it. There's a feature on Intel CPUs called, what is it called? Where you can basically directly inject a nested page fault into the guest.
EPT violation.
EPT violations, yes, that's the one.
So you can abuse
You could
the VE
use
handler
EPT violations, but you can't really, because EPT violations still need to inject a normal IDT-based vector, so you need guest enlightenment for it. But you could
Not
enlighten
necessarily.
the guest. If you have ideas on how to not have it, let me know. I don't want to be too hacky there. So yes, sure, we could trap on any load IDT instruction and then intercept like that.
I assume the SMI was so you didn't have to enlighten, but I was curious if you had
yes.
gotten to the point where you started to enlighten the guest.
Correct. As SMI, this path is basically a drop-in thing that just works.
Yeah.
And then all the accelerations can come later. So we can accelerate a lot. We could just given the right enlightenments on the guest, we could essentially make all of this a call. You could even patch the reads and the write, like the outls and whatever, the port.io things. You could just patch them.
You can use
in the guest.
alternatives.
Hi. Regarding the second benefit of live migration, so you mentioned the ease of passing the device information, the backend device information from the source to destination, but the other half of live migration is that you somehow need to synchronize the physical device and the destination to start from the same point.
Yes.
So while it's working, so that's the other half of what happens when it's working in the hypervisor. So how would you address it in this case? If
it doesn't, you have to have virtual like migratable hardware devices that on pass-through already allow migration.
So we still need to pass device state.
You still need the device state of the pass-through device, but you don't need the device state of the emulation device.
I see. Okay, thank you.
Creative stuff. I'm blaming this on my limited imagination, but I'm struggling to see the use cases where this is desirable instead of just passing through the device straight away. So if you need a real device to use the idea with, what other use cases you see that this is more interesting than just doing straight device pass-through?
So this is for cases where you need to, so there's a couple of different areas, and again, we should just do a BOF later on this day. There are a couple of cases where this is important or interesting. Say, what if you want to move all of the X86 emulator out of KVM into some other entity? What if you want to move the IO APIC out of KVM into some other entity? What if you want to support a legacy device configuration that you don't have in hardware anymore? So you need to, say, implement Virtual 0.9 on top of whatever your most amazing Mellanox adapter that you got now. You can basically use this as a mechanism to do legacy emulation without all of the attack surface that usually legacy emulation gets you. That's the big selling point in my book.
Hi, I've got a half question for you, Alex.
Yeah.
Your slides are missing in the KVM forum site.
Sorry again?
Your slides are missing from the KVM forum site.
They are. I'm going to push them. I did not want to push incomplete slides.
Okay. That's not fair.
Okay, thank you.
Thank you.